So welcome back, Level 2 physicists, continuing on with this last kind of subtopic in the Level 2 mechanics paper. And today we're looking at an introduction to the concepts around energy. Okay, so here's just two examples. Okay, so we've got the runner and a diver. So we've got to ask, well, who actually has more energy and how are we going to determine that? Okay, so this is where equations can become quite useful. So there's many types of energy. They range from gravitational energy to chemical energy, which you see in chemical reactions, to the energy of moving, kinetic energy, or even radiant energy, which we get from the sun. In terms of kinetic energy equals half times the mass times the velocity squared, or EK, that subscript being kinetic energy, equals half mv squared, where the kinetic energy is in joules, the mass is in kilograms, and the velocity, of course, is in meters per second. So if we go looking at least the potential energy, which one will have more mass will determine which one has the more potential energy. So the big sumo wrestler should potentially have more potential energy than the skinnier diver. Okay, and also considering this, which one has more potential energy? Well, you should determine that the one which is higher off the ground actually has more potential energy as well. Okay, so the reason why is because of the following equation. So the PEG, which is G is lowercase for gravity, equals mass times gravity times height. Okay, or delta EP equals, so this is the change in potential energy, equals mass in kilograms times G, which is 9.81 newtons per kilogram, and delta H is going to be in meters, and I forgot, of course, being in energy, gravitational potential energy will have the units of joules. So, going back to our original question, whom has the greater energy? So our diver, if we use the equation of the change in gravitational potential energy as being mg delta H, if you plug in the numbers, that will be 2,943 joules, whereas the runner will be kinetic energy equals half mv squared. Again, plugging in the numbers, it will be 2,941 joules. So our diver just has more energy, at least more gravitational potential energy. Another energy that we looked at the start was the concepts around elastic potential energy, which we see also in springs. As you pull back, as the pullback distance increases, the elastic potential energy also increases. And I did mention springs, and that relates us back to Hooke's law. So the force, of course, we know equals, the restoring force is negative K delta X, okay, and K is going to be in Newton meters. That's that spring constant. So as the string is stretched, there is that restoring force, which is given by that equation, which is proportional to the displacement. Okay, and that also means there is potential energy stored in the spring. So the work done by the force, okay, we looked at work in the previous lesson, is stored in the system as potential energy. Okay, and this potential energy, or EP, is equal to the work being done by the stretching or compressing of the spring. Okay, remember, work is that force being applied over the distance or of that spring. Okay, the expansion of the spring. Okay, so as we know, the force equals K delta X. Okay, that's being applied. We can calculate that, therefore, the stored elastic potential energy with the work equation. So the work equals half the change in the extension times the force being applied. So work equals half delta X times K delta X, because force equals K delta X. So work equals half K delta X all squared. Okay, and that's also going to equal that potential energy in the spring. Okay, so if we get those equations, then force equals K delta X from Hooke's law, and the potential energy of that spring is going to be half delta X squared. Okay, and that is probably enough for today's lesson. as we continue on with our journey in energy.